Hi and welcome. In this video I want to talk about a project that I did recently. I've actually had a lot of time to do some projects and I want to show them in the upcoming videos. This one is a plugin for the Unitrend UT61E multimeter, and the Unitrend has, it's actually a pretty decent multimeter precision-wise, but it has one feature that I really like about it. It has an optical interface back here through which it transmits the current measured values, and by default it comes with a cable that connects to RS-232. The RS-232 is, or basically the optocoupler in this adapter is parasitically powered. And this is kind of annoying for some purposes. I mean, it works if you have a true RS-232 port and if the driver is properly configured, but if you have, for example, a USB converter, you may run into problems and so on. So I decided to build an Ethernet adapter for this. So basically, I took the RS-232 cable, changed the parasitically powered setup to get its power from the mains, and this basically plugs in here. It transmits the measured values that are acquired over the multimeter through the Ethernet port using an ENC28J60. It's a microchip controller that I wouldn't ever use again because the datasheet is just messy and it's a horrible collection of silicon bugs, this device, so I'd rather recommend the ENC424J600 if I'd do this again. But I'm just going to summarize what I did in this project, what the problems were, and how you can build your own.
So one of the first things that I did before starting the conversion was to get the adapter running in its stock configuration. This means for this adapter that the baud rate was 19,200 baud and 7 data bits, odd parity, and 1 stop bit was used. After I had it set up, I just fiddled a bit with the control lines until it started to work. One thing that you notice when you take this apart is that there are 2 control lines, this here and this here, that are just used for the parasitic power supply. And when you take the connector on this side here apart and see where those go, you will see that the positive power supply connects pin 6 to pin 4. Pin 6 is the data set ready and pin 4 is the data terminal ready. And about the same thing happens here. Pin 7 and pin 8 supply the negative supply voltage for the device, and 7 and 8 are request to send and clear to send. The other 3 lines are just pin 2, 3 and 5. Pin 5 is the standard ground pin. So this is clear, the yellow cable on this side was ground, and 2 and 3, this here and this here, they just receive and transmit data. Note that the opto interface that I have does not actually have the means to transmit data. It doesn't have a sending diode on that side. But the multimeter appears to have a receiver on its side. I haven't tried out if that works, however. So basically, if you've come so far, you know that the cable that in my case was orange, this might be different in your case, supplied the positive supply voltage, the green cable supplied the negative supply voltage, and the brown one was actually the data that was sent by the multimeter and returned to the PC, and yellow was ground. So we only have those 4 lines that are of interest. White isn't connected at the opto interface, so we don't need to do anything with that. We can just ignore it. Then I just made an educated guess about how the UT61E does the optical data transmission, and it works like this. There is on the multimeter side an IR LED, and the IR LED basically sends out light, and the light is received by the opto interface that we're trying to convert to Ethernet. So on the receiving side here, there is a opto transistor. This is an NPN type, has a collector and an emitter, and the difference between an opto transistor and a regular transistor is that the base here is not connected to a wire, but it is basically exposed, and this means if infrared light or if light of the correct wavelength hits this exposed base, there is a base current that flows down here and the transistor turns on. So basically it's just like a regular transistor, but instead of a cable here, it's connected to a light source. So this emitter here in the adapter is undoubtedly connected to the negative supply voltage, VEE. In our case, this is -9 volts. And the collector has a pull-up resistor. How large this exactly is doesn't really matter. It's connected to VCC, and this is plus 10 volts in our case. Now this line here is the RX line, or actually more properly it's the inverted RX line, because this thing is meant to operate with a standard RS-232, and if we want to convert this to TTL levels, then we also need to invert the RX line, because the idle level for RS-232 TTL is plus 5 volts, but the idle level for RS-232 in the setup that it's supposed to work in the stock configuration is -12 volts. So this means that we can basically just change VCC from its 10 volts to plus 5 volts, and we can just change VEE from -9 volts to 0 volts or ground. So to make this signal usable with our microcontroller, the only thing that is left to do is just to invert this signal. But before we do that, we can just take a quick look at the oscilloscope if the waveform does really look like we expect it to look. And it actually did. If we have 5 volts here and 0 volts here, I just probed this is a probe of the not RX line after I switched the levels, the -9 volts to 0 volts and the plus 10 volts to 5 volts. And basically what you see is that the line is mostly on 0, and then there is a burst where there is data transmitted, and then it goes back down to 0 and stays there. So this basically tells us that we only need to invert the signal because the idle level should be 5 volts for a correct RS-232 TTL. Luckily, inverting the not RX line is really easy in hardware. All we need is another NPN type transistor. I used for this purpose a BC847. This is an SMD type transistor. It's actually in a SOT23 casing. If you're looking for a TO92 casing type transistor, you can use, if you're from Europe, the BC547, or if you're from the US, say 2N3904. So those are just very general switching transistors. And this here is connected to ground. This side is connected to ground. We need a resistor here. I chose 4.7 kilo ohms here. And we basically use a pull-up resistor here. I used 10 kilo ohms for this. And this here is connected to 3.3 volts in my case, because that's the supply voltage for my microcontroller. And here, this is the inverted output that I can feed into the microcontroller. So this little circuit actually fulfills two purposes. One, it inverts the not RX signal to become the RX signal, and two, it shifts the 0 to 5 volt signal to the 3.3 volt signal that my microcontroller could understand. So another thing that is unusual about the UT61E is that I mentioned that it uses 701 as a transmission protocol. This means 7 data bits, odd parity, and 1 stop bit. Now here's the picture from Wikipedia that shows the typical 8N1, which means 8 data bits, no parity, and 1 stop bit. You'll see that a transmission always starts with a start bit, and then here come data bits, one after each other, starting with the least significant bit here, so this is the 1 bit, this is 2, 4, 8, 16, 32, 64, and 128. And after this, 1 stop bit. Now in 701, this is a little bit different, because since we only have 7 data bits, this here is not a data bit, it's actually the parity bit. And the parity bit basically is a little bit of a poor man's checksum over the previous bits. It basically, odd parity means is the number of 1 bits in the previous bits, is it odd or is it even? And that decides if this bit here is 1 or 0. So this is something to protect against very, very rudimentary transmission errors. So besides the Ethernet output that I had in my converter, I also wanted to output data on the serial line, and I wanted the data that is output to be output with a much more common 8-in-1 encoding. So since I need to configure my receiver with either this here or this here, I can't basically choose one for the receiver and one for the transmitter. I need to decide for one. And here's how I got away with using 8-in-1 for both, basically. If you configure 8-in-1 and the actual transmission is 701, the amount of bits that is transmitted stays the same. The only difference is the interpretation of this last bit here. And if you have selected 8-in-1, you will basically interpret the send parity bit as a data bit. So if you know this, you can handle that in software. You can basically do a bitwise AND with the value hex 7F, which basically truncates away the most significant bit, and you will end up with 7 data bits, and you can basically find out what the send parity bit was by ANDing with hex 80, which is basically only the most significant bit set. So that way you can kind of do both.
So let's have a look at the hardware. So this is the hardware. It's basically very simple. I just built it on a prototyping board. I really like to use those. And the ENC28J60 that I used was one that I had left over. It was just a Olimex header board. If you try to replicate this circuit, I would strongly urge you not to ever use the ENC28J60 because it's just a piece of garbage. I cursed a whole lot about this IC because I programmed the driver for this and actually the whole network stack and everything myself. And it has a lot of very annoying silicon bugs that the ENC424J600 doesn't. Anyway, the circuit is really easy. It's just an ATmega 8 here, which is supplied by a L1084. This is a LM317 variant that has a low dropout voltage. This generates the 3.3 volts which are needed for the ENC network chip, and the AVR is actually also supplied with 3.3 volts.
So just a quick word about why I used the L1084 instead of the much more readily available LM317. Basically both devices do the same thing. They're adjustable voltage regulators, an in, out and adjust pin here. And through a resistor combination between out and adjust, you can basically select the output voltage. Now, there is one thing that is called the dropout voltage, and what it refers to is the minimum difference between the input and the output voltage. So in my case, the input voltage was 5 volts, the output voltage was 3.3 volts. So the difference between the two is 1.7 volts. So this is taken from the LM317 datasheet, and I have noted the values that we use in our example here. We have an input of 5 volts and output of 3.3, and the difference is 1.7 volts. And basically there is a dropout voltage chart in this sheet that tells you at which temperature the input-output differential, which is exactly the difference between those two values, may get, and at which point the device starts to not work reliably anymore. So we have a voltage differential of about 1.7 volts, so we're around here, and the chip that we used, the ENC28J60, is actually quite current hungry. It has about 150 milliamps. So we'll take this chart here, which is for 200 milliamps. And we will see that we have a break-even point at about 0 degrees Celsius. At 0 degrees Celsius, the dropout voltage rises above our 1.7 volts. This means our device only works at room temperature if we had chosen the LM317, and would not work below 0 degrees Celsius. If you have a low dropout variant, like the L1084 that I chose, this dropout voltage is much lower, and you don't have a problem at what temperature ever. So looking at this chart, choosing an LM317 might have been okay if you used it at room temperature, and since the current is also lower than 200 milliamps probably, we would also have some safety margins, but I had this L1084 lying around anyways, and I chose it because I think it's better to be on the safe side. So just a quick word about how the whole thing works together. Let's say we have our UT61E here, and we click in the optical connector, which is connected to a wire, and the wire is connected to our converter. The converter is plugged into mains and also into Ethernet here. This is basically the way that is set up, and the UT61 will transmit data via RS-232 here into the converter. It's an ATmega 8, and the ATmega 8 will send it out through the ENC28J60 over the Ethernet. The way this works, or the way the software stack is laid out, basically at the lowest layer there's the ENC28J60 driver, which is really a crappy chip. I think I've mentioned it a couple of times. Please don't use it ever. I just had that lying around. This one does basically raw Ethernet frames. On top of that, I put a very slim IP stack, and on top of the IP stack I put some very slim UDP stack, and the UDP is needed because the whole device does DHCP. DHCP is a UDP protocol, and the way this works is when you first turn it on, the device acquires an IP address via DHCP and actually takes care of renewal and stuff like that. And every time that it receives a valid RS-232 frame from the UT61E, it decodes it properly and turns it into a format that is much more easily readable. And then it sends those out via UDP broadcast to the broadcast address that it received via DHCP. So that way you can actually have more than one multimeter with more than one converter plugged into the same network, and you will be able to receive data from all of them. So just a quick demonstration that it actually works. Here is the source code, It's all open source if you'd like to peek or poke around in the UDP stack, or if you'd like to have a look at how I do the UT61E protocol, encoding, decoding, how I do the 8N1, 701 conversion and stuff like that. My thanks go to Henrik Haftmann of the TU Chemnitz, who put up a really fantastic description of how the UT61E protocol works. This is basically what I implemented, was very straightforward. In the open source code you'll also find the ENC28J60 driver that I used. Maybe you want to use that, but I'll say it the 100th time. If you have any chance, try to avoid this chip. And a small Python script which actually does the decoding. If you run it, it just listens for the broadcast packets from the device. Currently there are none because the multimeter is turned off. If I turn it on, you see that it immediately starts broadcasting values with an associated MAC address, so you can distinguish more than one if you have them connected to your network, and with a Unix time-t timestamp and the according units. If I put my hands on there to induce some voltage, you'll see that the display changes. If I change to ohms mode, you'll see that it's currently overflowing. I'll also touch the leads here. You'll see my resistance. Let's measure my capacitance. Right. Also supports all kinds of relative min-max type of stuff, but you can check that out for yourself if you like. That's it from me. I hope you enjoyed the video. Hope it was useful to you. If you have any questions or thoughts or improvements or whatever, please let me know. And thanks again for watching. Bye.